My name is Jeff Hickey. I'm an associate professor in geography, and I'm organizing a seminar series along with Beth Newingham of College of Natural Resources, Sanford Eigenbrode, College of Agricultural and Life Sciences, and John Abatzoglou, who's also in geography. We have a seminar scheduled, I think, almost every week. And so the way to get announcements is by looking at the web page. That's the most current thing. I'm distributing announcements as widely as possible, so apologize for getting multiple ones, but if you aren't getting those announcements and want to be on an email list, send me an email. We also have a what's called a Circus group that occasionally gets announcements, and I'm going to pass around a list. And so sign up with your email address if you want me to add you to that list, and you'll get this week's announcements as well as other climate-related announcements. Let's see, we're recording the seminars, as you can see in the back, so they'll be available to be reviewed or viewed by people who aren't here pretty quickly after today. We're sponsored by a number of folks. We're bringing in visitors, and the recording is costing us some money, so we'd like to thank the College of Natural Resources, the College of Science, the Department of Geography, the REACH project, and the Vice President for Research for funding that. Almost done with the announcements. Ken Bird is organizing the Renfrew Interdisciplinary Colloquium, and they're going to have some climate-related colloquia this semester, so look for announcements from Kenton on that. And we might share seminars if it's appropriate. And just to announce next week's seminar, because some of you may have to leave before the end, and that's Sanford Eigenbrode, who's going to talk about agricultural pests in the Pacific Northwest. So today we're having Dr. John Abatzoglou. He received his PhD in Earth System Science from the University of California, Irvine in 2006. He came to UI in 2009 from San Jose State University. His bio reads, John's research interest spans the weather-climate continuum in both basic and applied scientific questions. He conducts climate-related research specific to the American West and is engaged in several aspects of applied climatology and meteorology specific to wildfire, agriculture, and hydrology. John's research portfolio includes a better understanding of climate variability and change and associated impacts across the Western U.S. He's published numerous papers in climatology journals, as well as in Science and Nature, PNAS, and he won the University of Idaho College of Science Early Career Award last year. So he's going to talk about catching up with climate change to save science.
Great, thanks, Jeff. Jeff did a fantastic job, obviously, advertising this. So that's good. I was thinking the only other time that this room is going to be this crowded is if it's exam. So that's nice. So this is climatologically the coldest week of the year, typically around here, but yet we're going to talk about climate change. And it's interesting because if you think about, the time of the year we might actually be thinking about climate change, this might not necessarily be it. However, there are certain news media outlets that actually end up reporting disproportionately about climate change when it's cold. Okay, and this is something that we've seen recently. They've also sort of developed these fictitious names for winter storms and created seemingly new terms. The problem is that these people really didn't take our introductory course in physical geography. Number one, winter is cold, and number two, the polar vortex is in the stratosphere. What we really saw was a large amplitude wave, but you see that doesn't really come off the tongue. Okay. What I want to do with my time here today is to bring you guys up to speed on where we are in terms of our knowledge of climate change, and also give you guys a little bit of an idea of what folks are doing at the University of Idaho on climate change itself. And we're fortunate enough to be doing this at a time where we've had some really large international and national synthesis on climate change. And the couple documents that I'll be referring to today include the Intergovernmental Panel on Climate Change, the report, the Fifth Assessment Report, which the first product came out in September. And just as a background, the IPCC, most of us have probably heard that term. The IPCC does not conduct research. They don't take observations. Their job is to synthesize the state of the science when it comes to climate change. And they put together this document that is perhaps the most well-reviewed, peer-reviewed document known to man. So it undergoes quite a bit of scrutiny, and in doing so, you have to get an agreement among scientists, so you might leave off certain sites, but it is a very, very thorough document, something on the order of, I think, 1,000 pages per report or so. So what I'll be talking about today comes primarily from the physical science basis. The additional reports will be released this year. The second report is on impacts, and then the third report is on mitigation. So we'll be seeing those make media waves in the coming year. So this was the fifth assessment of the IPCC report. Okay, and I'll be bringing you through a little bit about the history of the IPCC and also the history of what we know about what we actually know about climate change. So we're sort of bringing you up to speed here. Maybe we've learned something new with this latest report. In the report, there were 3 statements that came out that sort of synthesized what is known about climate change to date. And basically, these statements are things we've heard before, that warming in the climate system is unequivocal. We can see it throughout numerous aspects of the climate system. The human influence on climate is also clear, and it's extremely likely that the human influence is the cause of the warming that we've seen globally over the last half century. The document goes on to talk about numerous aspects, including modeling the future, and what I'll do today is provide you a little bit of a sort of a glimpse in what that looks like. And that's sort of an international view, big picture view of the climate and what we know about climate change. There have also been documents that have been put out at the national scale and at the regional scale recently, and these have included authors from the University of Idaho, Dr. Hickey and Stanford Eigenbrode, participated in the National Climate Assessment. So this takes a look at the United States and also looks at things from a sectoral perspective. And there was also a report that came out specifically for the Northwest that also included folks from the University of Idaho. So we are participating in sort of understanding what the climate system is doing and its impacts across various sectors. Okay. So there's a lot of things that have come out about climate change. I want to talk about 2 of them and specifically about some of the science behind them. This is one of the figures from the IPCC report. It basically is showing us sort of an annual time series of global mean surface temperature, and then also showing that in terms of the decadal average. The different colors there are different observational data sets. The message is basically one is that no matter what data set you're really looking at, it's hard to deny that there has been an increase in global mean temperature. That's what you should see. What actually has ended up coming into the public, this is sort of the public view recently, is if you look at that last, say, 15 years of temperature, you might argue that we haven't seen any more, right? So this has been a source of public discourse on climate change. And when we hear these media reports that come out talking about how cold it is, it's typically one about where is climate change, okay? And if you look at maybe the last 15 years, put on blinders, you might say, oh, okay, maybe, maybe not. So that's an interesting challenge, and it's one which scientists are actually have some good answers to address what we've seen recently. If you look at this time series as well, you might find other time periods over the last century where we actually have seen plateaus, pauses, or hiatuses in warming. Okay? And those are relatively short-lived, so take a bit of what you will. But it has made quite the rounds in media the last few years. And one of the problems with this particular way of looking at things is when we talk about climate change, we're trying to project that into the future. And people have looked at sort of what's happened the last, say, 15 years and seeing, no really obvious warming, and they basically go, why should I really care about what those trajectories look like in the future, right? So that has some problems to it, but it's a nice sort of nugget for folks who might not necessarily buy the idea of climate change to point to. Okay. So what are some of the reasons for this pause in terms of warming we've seen globally? And when I showed you this picture of global mean surface air temperature, that's just one of a number of indicators that you could look for when you're looking for change. So there's a few things that we'll go into. One is that since around 2000 or so, we've actually seen an increase in atmospheric aerosols. And aerosols are these fine particulate pieces in the atmosphere that are microscopic. They reflect radiation back out to space. If you have more aerosols, you're going to reflect more radiation. You might cool things down. That's one possible idea. We've also heard about the weak sun that we've seen recently. The last solar minimum was actually the lowest solar minimum that we've seen in 50 years. Okay? And we've also seen interesting changes in the stratosphere, a reduction in the amount of water vapor in the stratosphere. And what we know is that as you put greenhouse gases, and water vapor is one of them, higher and higher up into the atmosphere, they end up having a stronger impact there. So those things have been happening, and they might end up modifying the amount of heat or energy that the Earth's atmosphere is trapping. Small amount. Okay. We've also seen natural climate variability. So I think in some people's mind, when we look at climate change and we're not aware of what the natural climate system is able to do, we think that it's going to be some sort of a monotonic increase in temperature year after year. When in fact that's not the case whatsoever. There's a lot of noise and natural variability in the climate system, some of which we can explain and some of which we cannot explain. What we've seen in the last decade is sort of a series of La Nina events. La Ninas tend to be associated with cooler ocean surface temperatures and release less heat into the atmosphere. So what ends up happening is that you actually do not flux as much heat back up into the atmosphere. More of that heat is retained in the ocean. Okay? So we've heard these reports about the lack of warming over the last 15 years, and people have been trying to figure out why. And some of this explains that if we think about where our observations are globally, they tend to be located in sort of the mid-latitudes. Even if we spread things out, there are certain areas of the globe where we have poor measurements. And one recent study actually shows that if you take into consideration what's been happening in the Arctic the last 10 years, you see a pretty significant warming that's more or less along the lines of what we've seen over the last 50 years. Okay, so that's this idea that warming is not going to be geographically uniform. It's going to have a spatial structure to it, and in fact, that is true. And what do we know about what's happened in the Arctic recently, specifically during the summer months? Well, we've seen this dramatic decline in Arctic sea ice extent, particularly the end of summer. We look at this in September. We've seen a significant drop-off in summer Arctic sea ice extent, actually far more than what we project with our climate models. Okay, and you can note here from 1998 to present, significant reduction. Turns out that in the Antarctic, that's not necessarily occurring. The Antarctic is sort of holding its own ground, but if you combine the two and you look at total area or volume, the trend is one dominated by the Arctic. The other graph that I have on here on the left-hand side is looking at another measure of global energy. And this one's actually showing us an integrated measure of ocean heat. Okay, so surface air temperature is one way to sort of take the temperature of the planet. Another way to take the temperature of the planet is to measure the temperature of the ocean. And what I'll point out to you is here is 1998. And what we see here in the purple line is actually if you integrate over the total depth of the ocean, and this is down to I think maybe this is this is down to maybe around 2,000 meters or so. What you see is that a lot of that energy, a lot of that heat is actually in the ocean now. Okay, it looks very, very different. So those are some ideas on potentially why we haven't seen warming. A lot of that's natural variability. We expect that this hiatus or pause is a temporary one, and that we will see the more obvious signs fairly soon. And in the meantime, we passed a historic barrier last year in terms of atmospheric CO2 concentrations. I believe during April or March, we passed 400 parts per million. of CO2 in the atmosphere. And that's a benchmark. People talk about benchmarks of 350 parts per million. And it turns out that that's important when we think about where we're heading in the future. This record from Mauna Loa goes back to 1958, and it certainly paints the picture of what we've seen in terms of increases in atmospheric constituents of greenhouse gases, CO2, and they're also measuring methane there as well, which is another powerful greenhouse gas. Okay. So we've seen this increase in atmospheric CO2. We've also seen changes in where that carbon is coming from. And this is a big sort of task in terms of trying to do the accounting work of carbon in terms of the natural carbon cycle and then the perturbed carbon cycle, the human modified carbon cycle. So we've seen increases in fossil fuel. That's putting an additional 8.5 gigatons of carbon up in the atmosphere per year. Land use change contributes another gigaton. And not all of it actually goes into the atmosphere, it actually remains there. Only about less than half of it actually remains in the atmosphere. The other components are going into the biosphere as well as into the ocean. And how do we know it's going into the ocean? We have pretty long-term records now of oceanic pH, and what we're seeing is oceanic pH dropping. Okay, the ocean is becoming more acidic, and that's CO2 converting into carbonic acid in the ocean. Okay, so here's my equation. I'm showing an equation. Okay, this equation is basically trying to look at how the surface energy balance of the planet works. Okay, so the way you think about this is we have a term here which is the solar output. What's going to control the temperature of the planet? You know, your solar energy is going to be a big contributor. The amount of radiation, solar radiation that's reflected back out to space, that's going to be an important contributor as well. And then we have this term here, which is basically the greenhouse effect. It's sort of the emissivity of the atmosphere. Okay, those terms on the left-hand side are basically the inputs in terms of energy. On the right-hand side, we have the surface temperature of the planet. That's this TS here. Okay, so don't worry about the right-hand side. Worry about the left-hand side, because if we change this left-hand side, what's going to have to happen is that right-hand side is going to have to balance. And the way that balances it is if you add more energy to this left-hand side, you're going to have to increase your surface temperature. So what do we know in terms of changes in some of these variables over the past 200 years or so? The IPCC has done the job of synthesizing what we know. And we're going to express these things in watts per meter square. Okay. What we know is that the solar variability does occur. It occurs over an 11-year cycle, and there's also some longer-term fluctuation inherent in that. We've seen more solar flux, solar energy now, but that number is pretty small. It's only about a 20th of a watt per meter square. Okay. We've also seen changes in aerosols in the atmosphere. Right? This is associated with things like the Industrial Revolution. If you look at the air quality situation in parts of Asia today, it's not too hard to understand where those aerosols are coming from. But collectively, aerosols have had the effect of reducing the amount of energy reaching the surface of the planet by about 1 watt per meter square. Okay, so those two terms together, we're in the negative, which would result in the cooling. But the big thing that has changed is right here in this atmospheric greenhouse gas component. And we've seen increases in CO2 and other constituents, and that's resulted in about an additional 3.2 watts per meter square added to the system. When you combine all those things together on the left-hand side, what we're left with is that we've added an additional 2.2 watts per meter square to the surface energy budget. Okay, and the only way that that's going to balance out is if we warm up surface temperature. Okay. Another really big, important question when it comes to climate change and thinking about the future, we're seeing CO2 increase. It's sort of like a runaway train. That's quite a challenge to stop. And let's just say that CO2 doubles. Okay? The big question is, what is the response of the climate system to a doubled CO2 environment? Is it going to warm by ½ degree, 2 degrees, 4 degrees, 6 degrees? It's a pretty important question to get at. Okay? So one way in which we can understand basically how much the system will respond to a given forcing is something that we call a sensitivity, the climate sensitivity. And if we look at what this answer should be, if you actually went through some of the equations and you solve for this, what you find is that the planet would warm about just less than 0.2 of a degree Celsius per watt per meter squared. Okay, that's in a system, that's in a vacuum though. That's in a system with basically no interaction between the atmosphere and other components of the climate system. But what we know is that if we warm the climate system up, what's going to change? What are some things that might change? Boreal soils might change, and what's that going to do?
Decomposition of forests that are giant, thick mats of vegetation.
And they'll reflux back into the atmosphere. So what we're talking about here is one example of a feedback back into the atmosphere. One of the examples that is probably the easiest to understand is what's called the snow albedo feedback or the ice albedo feedback. Basically, think about the periphery of an ice sheet and warm things up a little bit, you're going to melt that periphery just a little bit. And when you do that, you're replacing a very bright surface that reflects radiation back out into space with a very dark surface. Okay, that's going to amplify the effect of that change. So this is really the holy grail in terms of trying to understand where we're going to be in 50 years and 100 years. On a global scale, on a regional scale, it turns out to be a little bit more complicated. But just how much is the climate system going to warm? It turns out that we've been coming up with estimates of this climate sensitivity, how much the climate system would warm to a doubling of CO2 for quite some time. And the initial estimate here is one that does not include sort of those climate feedbacks, and that's one where you basically get a change of 0.2 Celsius per watt per meter square. So under that situation, if you doubled CO2, doubling CO2 is about 4 watts per meter square, you're less than a degree Celsius change in temperature. Not a very sophisticated way to go about things, but sort of a first approach. Other estimates have come into place since then that have incorporated some of these feedback processes, and also modeling studies, paleoclimatic studies, and observational studies. And there's a range of outcomes that they yield. And the ranges are shown here. You can go back to 1980s, sort of the first generation climate models, and you can look at them over the previous IPCC reports. And the ranges here are somewhere between around 2 and 4 degrees Celsius. There might be some models that are way up here. There might be some that are lower. But the range that we're looking at here in terms of, representing 2/3 of the samples, somewhere between 2 and 4 degrees Celsius. And what's interesting to note here is that we've advanced science through time. Okay? Climate science, like many other sciences, is continually advancing. We're learning new things. But we're still pretty set on this 2 to 4 degrees Celsius warming for a doubling of CO2. Okay? So what have we learned recently about how sensitive the climate system might be? Well, one thing is that we have seen in the past decade, we've seen increases in aerosols, okay, some of those other attributes that I mentioned before, and those have acted to reduce the amount of radiative forcing. Okay, so that might indicate that the climate system is maybe less sensitive. The latest IPCC report also discussed climate sensitivity, and they basically revised the previous estimates. In the last report, it was somewhere between 2 and 4.5, and they said it was 1.5 to 4.5. Not a big deal, right? But it turns out that several people got a hold of this and went, wow, they revised the estimates, and the climate system isn't as responsive as we thought. Well, not really. And then recently, we've looked at some of these models in more detail, and what we found out is that some of the models that tend to represent a really, really low number in terms of climate sensitivity, they aren't capturing the way in which clouds in the subtropics form. And they end up actually simulating more clouds in the subtropics in a warming atmosphere, which reflects more radiation back out to space. And it turns out that that's probably a bad estimate. So we're looking here at probably that number going up. The idea is that these things do change through time. Science comes out, changes numbers just a little bit in either direction. But when we look at this through time, when we look at the latest IPCC report, we're still looking at basically the same story. So that's interesting, and that's sort of maybe, I don't know if that's comforting or not. If we saw these things wildly changing, maybe you'd feel better if there was no change in temperature, but they're pretty consistent through time. So that's an interesting outcome of the report itself. So climate science, again, is like other sciences. It's evolving. We're learning new pieces. It really integrates a lot of sciences together. So more and more, it's incorporating information about the carbon cycle, interactions with the carbon cycle. And this is maybe where we are today in terms of understanding climate change. And so we're filling in pieces to this puzzle. And we may eventually fill in most of it, probably never all of it. Right? But with climate change, we're trying to look into the future and make decisions about what's going to happen in 50 years and 100 years and maybe better prepare ourselves. So, do you basically wait to solve the puzzle until it's completely filled in? Right? When do you decide what to do? Sort of where we are right now. So I want to talk a little bit about the future and how we actually model the future and make these projections. The first thing that we need to do to actually model climate in the future, we need to understand what's going to happen to atmospheric carbon dioxide, methane, etc. into the future. And so there's a pretty extensive documentation on this, and they basically think about how changes in world population may evolve and how changes in technology and globalization may evolve. And there's not really any correct answer. But what they've come up with are a few different scenarios of how the amount of carbon dioxide, et cetera, are going to change in the atmosphere. And these have been contextualized in terms of that radiative forcing term, which is basically the extra energy added to the system. So 2.2, I mentioned that term earlier. That's where we are today. And the scenarios that I will focus on today are basically a scenario where we sort of continue sort of status quo, basically no action, and that's this scenario here shown in blue, and basically that means an additional 8.5 watts per meter square by the year 2100, and you can see what that is in terms of carbon dioxide equivalent. The other one that I'll focus on is 4.5 here, RCP 4.5, and this is a future where you can see that around, say, 2050 or so, the radiative forcing plateaus. That actually means that carbon emissions drop substantially, okay? Because carbon and methane, they had a long lifetime in the atmosphere. They're going to hang out for quite a while before they come back down. Okay, so that's another future. We'll look at those two. They're not the only possible scenarios, but they do give us a sort of range of how to look in the future. Okay, and one way I like to put this, maybe in terms that are a little bit more palatable, here's where we are today. We basically added one of these incandescent, don't get caught with them, light bulbs every 20 by 30 square foot on sort of the face of the planet. And here's where we're going. This RCP 8.5 is the 5 light bulb scenario. Okay, so it may seem like a lot of energy, it may seem like not a lot of energy, but that's where we're going. Okay. So how are we going to project the future in terms of climate? We don't want to extrapolate, probably not a good idea. If you extrapolated, especially using the last 15 years, you would say no, there's no change. Some people are tempted to do that, bad idea. Okay. Instead, what we try to do, we can't actually go out and perform experiments on the planet. Maybe we're doing that already, but we can't really see what the result is until maybe much further down the road. We're trying to colonize planets. It's not working so well right now. The best thing that we can probably do is to try to model the system. Okay? And modeling climate is pretty complex. You have to model atmospheric dynamics. You have to model biogeochemistry. You have to model the hydrologic cycle of the ocean and how they all interact with one another. So these are some of the more complex models that we have. They're run on some of the more powerful supercomputers across the globe. And these models are based on physical principles. For example, the atmospheric model that's used here is basically the same model that we use for weather forecasts today. Okay? And these are models, they're not answers. Models are used to provide us with tools to make better decisions. Okay? So those are some important things to keep in mind. And models aren't always right. Sometimes people put in an extra 7 maybe. Okay. But that being said, we're not going to rely on one model. We're going to rely on many models. Okay, the IPCC report, there was an experiment that was done prior to the IPCC, which basically called for modeling groups around the world to run the exact same experiment with their model. So we have participation from around 40 modeling centers globally. They all run the same experiment. All that data gets imported to a website that's difficult to access, right, Catherine? Difficult to access, a lot of data, okay? But at that point, then we can start to perform experiments, somewhat like what we do maybe in biology, where we have a series of rats and you inject them with a serum and then you inject the others with sort of a control, see what happens. We can do this a little bit with climate models as well. We're not going to rely on one model or one rat. Maybe a bad idea. But we're going to look at the sort of collective signal from these models. And what we get in terms of looking at trajectories of global mean surface temperature are as shown here. And again, the two that I'll focus in on are the RCP 8.5 and the RCP 4.5, red and maybe light blue there. Okay, so what you can see, first, there are a couple things. One is that regardless of what sort of trajectory we go along, we're expecting sort of this warming of on the order of maybe 1 degree Celsius over the next 25, 30 years or thereabouts. But what really ends up being important is what happens after around 2050. And so this RCP 4.5, again, the radiative forcing plateaus, the temperature somewhat plateaus, and you're left with a global increase in temperature of somewhere around 2 degrees Celsius with a substantial error bar. Right? Those are all those different models, climate sensitivity. There's some error bars in there, which is good. We're not expecting a single answer. On the other hand, for this 8.5 scenario, that's sort of the scenario where we're sort of continuing business as usual. The warming ends up being more than twice that by 2100. Okay, so you can think about what a world would look like if we warm things up by 2 degrees Celsius versus 4 degrees Celsius. And remember that's a global mean. The oceans warm quite a bit less than the land, which means the land warms quite a bit more than 4 degrees Celsius. The IPCC also produced this figure, which I thought is somewhat creative. The way to read this is think about the cumulative carbon emissions since 1870. Okay, so you start the clock in 1870, you count how much carbon has been emitted to the atmosphere through time, and then that's plotted versus the increase in temperature relative to 1870 or thereabouts. Okay, and the observations are shown here in black. You are here. Right? So we've emitted this much carbon, we've warmed things up about 1 degree Celsius. Okay? And then the rest are basically model projections. Okay? So this sort of helps contextualize how much carbon is emitted into the atmosphere through human sources versus how much we're going to see in terms of warming. So it's an interesting way of looking at things, and you can see that the red symbols here, which are the RCP 8.5, they move a bit quicker through time. Much like I suggested earlier that warming is not uniform globally, it hasn't been in the observational period. When we look at the projections from a global scale, we get a picture that looks something like this. So this is the future where we're expecting around 4 degrees Celsius warming. Right? But you can see that the warming is distributed in very obvious ways. The land surfaces warm more than the ocean surfaces. That makes sense. In the oceans, you can mix heat vertically. It's more difficult to warm water than land. And there's also a pretty significant amount of warming at high latitudes. Okay? And that's the idea that at high latitudes, you start to melt ice. You can actually result in a much bigger signature. In high latitudes as well, if you put more CO2 into the atmosphere, this is an area where the Earth is actually quite efficient at cooling off, very low water vapor, you can increase the amount of heat trapped there by leaps and bounds. So pretty significant here in terms of changes in temperature. Okay? And again, if I showed you this in the middle of summer, it might be a different reaction in the middle of winter, but it's been unusually warm here, and it's been muddy too, so that might resonate with a few people. Here's what things look like in terms of precipitation. So these are changes in precipitation. Again, the last 20 years of the 21st century versus contemporary period. Blues are indicating wetter areas. The sort of yellows and browns are indicating drier areas, and the first thing you might actually see is that there's a lot more blues and greens than browns in here. Okay, and that's generally true. We expect the globe to wetten as it warms. We see that through the paleoclimatic record. Okay? But again, things are not distributed geographically in a homogeneous way, and there's some pretty distinct patterns that show up. The ones that I'll focus in on here are these areas that are located around, say, 30 degrees latitude or so. Okay? These are basically just poleward of where our deserts are today, our global deserts are today. Okay? And one thing we expect in terms of climate change and how it's going to impact precipitation is, one, as you warm the climate up, you're going to increase the hydrologic cycle. And that's the idea potentially of actually the rich getting richer, the poor getting poorer. You evaporate more water from areas like the subtropical oceans, and you transport that to higher latitudes or lower latitudes. Okay? Wetter, warmer in general. The other thing that ends up happening in a changing climate, if I showed you this picture here, what you'll see is that the rate of warming at high latitudes ends up being quite a bit more than that at low latitudes. And this sort of changes the strength of the temperature gradient, and that strength of the temperature gradient is going to influence the strength of the winds. So what we expect under enhanced CO2 climate is for the jet streams to typically track poleward of their locations today, which means that locations like in the Mediterranean and also in the southwestern United States that are just on the southern edge or the equatorward edge, I'll be fair to the people in the southern hemisphere, on the equatorward edge of the jet stream today as far as it dips equatorward in the winter, that's not going to dip so far equatorward under enhanced climate, enhanced CO2 environment. Okay? That might be a significant concern because there's actually a significant amount of significant population living in these parts of the globe where water scarcity is already an issue. The projections also span other variables that may be of interest. One is decreases in spring snow cover in the northern hemisphere. Makes sense as we warm things up. On the sort of periphery of the sort of snow-covered area, we're going to melt things. Okay? And then also in terms of the Arctic sea ice extent. And again, what I'll point out here is that the green is showing our observations, and what you can see is that that's actually outpaced projections thus far, but that all these projections are indicating a decline, and some indicating potentially ice-free conditions, sometimes, not necessarily every single year, in the end of summer by sort of the mid-century or thereabouts. So that's a global picture. Now I'm going to move on and talk a little bit about what climate change might mean for our region. More specifically, it's likely you're going to hear other talks this semester in the seminar series about climate change. So this can be maybe a basis for understanding some of those talks. Okay, so these are some maps that look very similar to what I showed you earlier, except they're broken down for the western United States. They're also broken down by showing you the change in temperature from an annual basis and precipitation in the annual basis to DJF, which is December through February, winter, although I think our winter lasts a little longer than that. Hopefully this year we'll have something beyond February. And then summer as well, JJA. And what you see is warming more over the continents. And in terms of precipitation, it's fairly interesting for our region. We're expecting increases in precipitation during our wet season, so winter, maybe in spring, but then a decrease during our dry season. So maybe that's a little bit of the rich get richer and the poor get poorer as well. Okay, and by the way, those are averaged over 28 models. Some models are predicting or projecting things that might look quite a bit different. This figure here is showing a projection of average annual temperature for the Northwest. This looks a lot like the figures I showed you earlier for the globe. But again, this is for the Northwest. It's a continental area. And what you see is, and this sort of alarmed me, I usually work in Celsius, and when you put in the Fahrenheit side, you go, oh, double digits. And that's sort of the median, sort of an average estimate from some of these projections, getting into around a 10-degree warming by the end of the 21st century, which is pretty substantial. Okay. Obviously, the scenario where we start to enact policy and change the amount of CO2 put up into the atmosphere or sequester the CO2 that is in the atmosphere, that one has, again, a significantly reduced rate of warming, particularly over the latter half of the 21st century. I'll also point out that we've been looking at these models across generations. So we've looked at the past generation of models and the present generation of models. And this is a complicated graph, but the story one here is that these two, the silver and gold, are the old models. The red and blue are the new models, the red being the RCP 8.5 and the blue being the 4.5. And what I'll show you here is the projections annually for winter, spring, summer, and fall. Because you might imagine that if we think about impacts, it might matter about what season we're speaking of. Okay? And we'll look at it really quickly, try not to pass out. Okay, no takers on that. And what you end up seeing is you see a lot of variability, but what sort of pops out to me at least is that the sort of more recent models end up predicting a bit more warming. And if you look at the seasonal distribution, the warming ends up being most acute, it's projected to be most acute during summer. Okay, so great, just the time of year when we want that warming to be with us. So that is one thing we see. Another thing you might also note is that no models are projecting cooling. Okay, there's a few road models that are down here. That might just be part of the natural variability because these models do have natural variability built into them. But by and large, we're seeing warming. I'll show you the same thing for precipitation. Again, I'm warning you, it's going to look nasty. Okay. But what we see for precipitation is, again, quite a big spread. We're not seeing uniformity in terms of the response across models. Not all models are predicting an increase. Not all models are predicting a decrease. But the general patterns are wetter winters and drier summers, sort of like what I showed you earlier. Okay. So what impacts might that have? You can think about those things. We'll probably address them later on in this semester. There's an additional sort of kink to the story here, and this is a recent article that Charlie Luce and myself and Zach Holden looked at. We were looking at sort of changes in stream flow in the Northwest, and we've seen a significant decline in stream flow. We've also seen warming, which is the current hypothesis of why stream flow has declined. But it turns out that if you look at precipitation records in the Northwest, most of them are located at low elevations, so they're not necessarily capturing what's happening in the mountains. But what we see is we see a very strong relationship between the strength of the westerly wind at around 10,000 feet elevation and the amount of precipitation in the mountains where water really matters. And looking at the last 60 years or so, we've seen a decline in the strength of those winds, which we're inferring to result in a decrease in the orographic enhancement in our mountains, less precipitation in our mountains relative to our lower elevations. And when we look at the models for sort of the heart of the rainy season, which we're in, believe it or not, they're projecting a slight decline. So they're also suggesting that we might see wetter conditions overall in the Northwest, but the winds might slacken just a bit, so that increase may not be as robust in our mountains where water really matters. Okay. And then finally, I'll talk about sort of an important project that the University of Idaho is participating in with part of the Northwest Climate Science Center. We are linking together, we're sort of looking at the future integrated scenarios of climate, vegetation, and hydrology in the Northwest. In the past, this has been done sort of piecemeal, but what we're doing is we're doing an approach where we take a set of models, we run it through a hydrologic model, we run it through a couple different dynamic vegetation models, and we're sort of trying to paint this picture of what the Northwest might look like over the 21st century. And not just in terms of climate like I talked about today, but more of the sort of tangible impacts. So the University of Idaho, including Catherine, my postdoc, and others are involved on that. This is also with collaboration with the University of Washington, Oregon State, and the University of Idaho is playing a significant role in archiving that data and distributing that data, because those data sets are going to be pretty important for folks in the Northwest and actually nationally and internationally for understanding the response of climate change in the Northwest across various sectors. So I'll end with that, and I will remind us that it is winter, so it might be cold, and that's okay. But unlike, well, I would say the swine flu is still around, but we had this big sort of freak out recently. Climate change is not going away anytime soon. So you might hear that it's going away, but no, I don't think so. We have 30-plus years of modeling, and they sort of paint a coherent and consistent picture. There's still things we don't know about climate science, much like all other fields of research. And the University of Idaho is playing a significant role in climate change. Sanford Eigengrove will talk next week about what the University of Idaho is doing in terms of integrating climate change, agriculture, economics, which is a really important aspect across Idaho, Oregon, and Washington State. And I'll end there and have a few minutes for questions.
Yes, thank you, Dr. Ruff. A few points. If you're enrolled in this course as a student, please sign up here. We'll try and work on the classroom situation, but assume they'll be here next week unless you hear otherwise. And so I'll let you questions.
Any questions out there?
Could you expand a little bit, sorry, a little bit more about global dimming, masking, global warming, but aerosol?
Yeah, so do people know what global dimming is? Is this idea that sort of post-World War II, there was large-scale reindustrialization, a lot of that being fairly inefficient, putting a lot of aerosols or bright matter in the atmosphere. And during that time period, what we saw was actually declines in the amount of solar radiation reaching the ground, which has a number of impacts on growing crops and feeding the world. And so if you see a decline in the amount of solar radiation reaching the ground, but you have more CO2, then you can end up masking sort of the real effect of CO2 on the climate system. We've seen that somewhat decline in the last 30 years. So global dimming does not appear to be a significant player, but it is still an important player in parts of Southeast Asia with their what's called the atmospheric brown cloud phenomenon there. And so we're looking at ways of trying to identify better fuels that folks are using there. There's a question over here.
I was just interested in mitigation. People at the University of Idaho are moving beyond just looking and charting out futures, businesses, versus sort of a geoengineering approach and all the strategies and pitfalls perhaps.
No, we just like to talk about bad news. I think that there are some people at the University of Idaho working on mitigation. I don't think necessarily geoengineering, but I would imagine that there are folks that are working on aspects of carbon sequestration. I know there's a faculty member in physics that also is working on aspects of mitigation, but certainly that's the next step because the work that I do is just a report on what I was saying. So that's an important question.
Have you published your regional projections for the climate change?
No, that's a good question. We will be doing that, though. I'm glad you asked that. I will report back to others.
Has anybody come by the temperature increase that they talk about drought?
Yeah, absolutely. Yeah, so it's water scarcity. Drought can be defined in a number of ways depending on what impact you're thinking about. Certainly people have looked at things like soil moisture, maybe integrating that. If you think about longer term effects, those have been modeled. People have tried to model projected changes in drought, and those end up being quite significant in areas like I showed in the Mediterranean and the Southwest, where you see both increases in temperature and decreases in precipitation. So those are important attributes that we're looking at.
Question? Can you say a little bit more about the so-called polar vortex and what it was and what it wasn't and why it doesn't disprove global warming?
Yeah, so the polar vortex is part of the circulation in the atmosphere It's the idea that it's cold at the pole and it's warmer in mid-latitudes, and between that gradient you end up developing a strong wind that goes around, sometimes called the jet stream. And it's actually really, really strong in the stratosphere. And that polar vortex is super important for, in the southern hemisphere, in developing their ozone hole. So that basically traps that cold air in and helps to actually allow that air mass to be concentrated. The polar vortex is around all the time. What we saw was really a large-scale wave in the atmosphere. And so while the East Coast is, shivering, parts of the western United States are quite warm, and it turns out that the scale between those two locations is typically the scale of a large-scale wave in the atmosphere. So in the wintertime, I think often we hear news about cold in the east, and we're like, so, and they hear about cold in the west, they're like, I think we don't care.
Are most of you talked about some of the positive feedbacks, which are actually negative in terms of their impacts, but are most of the big, large known ones of those incorporated in the models, or is that a big area of improvement that yet needs to be looked at?
I think the one aspect of positive feedbacks, which basically act to enhance a signal like warming, the one big feedback that probably we're still working on is the carbon cycle. So I think you'll hear talks about the carbon cycle later, but that's sort of the big unknown, and also in terms of potential release of methane from the Arctic. If we somehow thaw the Arctic and the permafrost there could be a big flux of methane into the atmosphere, and who knows at that point. But I think those are parts of this current generation of models. They've made advances on the biogeochemical cycling and having an interactive carbon cycle, but I think that's where more of the advances will probably come.
One more question. John, could you address inertia in Earth systems? So these things are starting to change and may have direction, and it's complicated because there's a number of different systems, but could you speak about that?
Yeah, so inertia meaning that it's challenging to stop. The oceans, for example, have quite a bit of inertia. If you think about the amount of heat in the oceans, they're going to hold on to that heat for quite a long time. A lot of these greenhouse gases in the atmosphere, aside from water vapor, which goes up and down in like 10 days, CO2, methane, nitrous oxide, a lot of these other greenhouse gases, once they're up in the atmosphere, typically their lifetime is on the order of decades. So if you want to try to solve climate change and solve the carbon problem tonight, it might not happen. Although that's where the geoengineering piece comes in as sort of a quick fix of solving that. But the inertia, I think, is really coming from our oceans, and then also from these greenhouse gas concentrations in the atmosphere.
Okay, let's thank John again.